Hi, welcome back. In this lecture, I want to describe for the first time quantum version of a support vector machine. So I will be describing the general ideas behind it, and then in the next few lectures, we're going to look at more in detail the implementation of our first quantum support vector machine. So a quantum support vector machine is actually an ordinary support vector machine that relies on the kernel trick. The only difference with the classical SVM is that it uses a certain space of a quantum state as a feature space. So we're going to have a quantum circuit that allow us to go from initial classical state encoded into a quantum state through the use of quantum feature map that use a quantum circuit. So if we have a data space, two data point, x1 and x2, with a certain dimensionality, we can apply function phi to go directly into the quantum state. And then we are going to use this quantum state to calculate the kernel, that is the inner product of the feature map. So the major difference is the use of a quantum kernel function and quantum feature map. We're still going to keep part related to the optimization on the classical part. The only difference is really the fact that we are using quantum feature map instead of a classical feature map. So whenever we use the kernel trick, we only need the kernel function from the feature space. So we are going to use the quantum circuits to compute this quantum feature map and the quantum kernels. This work and this lecture is inspired from the work by the paper by Havlicek, Supervised Learning with Quantum Enhanced Feature Space. I strongly recommend it to read it, and it's posted on the Canvas page. So what is the strategy for the quantum support vector machine? Well, the strategy is doing everything fully classically, especially the part on the optimization, except for the computation of the kernel function, right? So for each training step, we are going to compute the kernel function on the quantum computer. There are basically three steps in our quantum support vector machine. We're going to take the two vectors in the original classical space as an input, and then we're going to map each of them to a quantum state through the use of a quantum feature map. Once we move to the quantum feature state, we compute the inner product in the quantum state directly and return a value to the classical optimizer. The feature maps are expressed as a parameterized circuit where we give the data as a parameter of the quantum circuit. The feature maps are nothing else than quantum circuits that are parameterized exclusively by the original classical data. And therefore, we prepare a quantum state that depends only on data. So in this slides, we see one feature map. Right, so we initialize our quantum computing system. In this case, it is 2 qubit with the state 0 and 0. So this is not the way that we input. Our input is actually defined as a parameter. So in this case, our point x1 to a feature map represented by a quantum circuit that is unitary, because all the gates are unitary in quantum computing. So the way to give as input to our quantum feature map is to use first a quantum circuit. I'm going to look at the specification of this quantum circuit in the next few lectures. That will take a state 0, and we apply a quantum circuit that depends on x1, that is our classical input. A feature map phi lowercase is implemented by a circuit phi uppercase that will depend on some classical data in the original space. So our feature map, this is our function. To express it, we are going to use a quantum circuit phi that will take as an argument, as a parameter, our data point x, and initialization is in the state 0. Remember that we start from 0. So with feature map ready, we can actually then take our kernel function to be, because we know how to take inner product, therefore how to calculate kernel function in the quantum state. So our kernel function is defined as follows. So we take the inner product of a phi on our data point A, and we multiply by phi. We take the inner product by phi on the second data point. We express this, so phi can be expressed by a quantum circuit. We are going to have here phi b. And so this is our cut, right? Remember that if we want to take the bra, we need to take the adjoint of our quantum operator, that in this case is expressed by uppercase phi. Because the quantum circuits are unitary by definition, and therefore if we take the adjoint of a quantum circuit, this corresponds to the inverse, that corresponds to apply the gates in the inverse order than the original phi. So this case, if we take phi lowercase of a, this is a bra, so we take the adjoint. In this case we take phi, that is the adjoint dagger. We use the symbol dagger, so that's why we have it here. Remember, this is actually a bra, so we need to take the adjoint, and then it will be quite easy to calculate, because for us the adjoint is also the inverse by definition of a unitary matrices. So the quantum kernel function relies on calculating this expression. This is nothing else the probability of measuring all zero after preparing the state that we have here on the slide. So we calculate this expression here. To compute the circuit for phi dagger, notice that we just need to invert phi, because the quantum circuits are always represented by unitary operation, as I said. So we're going to apply the gates in the circuit from the right to the left and the inverse of each of them. So I just want to summarize the quantum support vector machine. So we take first a feature map that will return a circuit F5 of x, where x is our input, and we are going to prepare this state. So 5 dagger, 5, and then check the measurement on the 0 for the pair of vectors on which we want to compute the kernel. And we return the probability of measuring 0 on all qubits. This is the last slides of this lecture, and in the next lecture I will provide more detail on how to implement quantum SVM. Talk to you soon.